Oh, I was gonna ask you a question, but I don't know.
Oh, yeah, no, I'm done. Yeah.
Um, so, the mental reading, when it says combine, do you mean you both of the programs to kind of come to a like optimal point? Or do you mean like pull code from like random walk and then program it all?
Yes, so in this case, when we're combining, we're basically running the one after another. But you can do that all within the same code. And so you're basically combining the two, basically kind of your two codes from parts A and B, and put them on top of each other. Because they're kind of there because the idea is that Monte Carlo and random walk are kind of good at different things. So Monte Carlo, the way it works is it kind of just jumps randomly around the whole. And so it's very good at kind of finding an approximate location. And it'll just jump randomly and it'll find a good spot. Oh, that's good. And then it'll say that, but then it'll jump. It doesn't do a very good job of once you find a good spot, let it improve in that area. Because usually when you find a good spot, and and a better option probably in that same neighborhood. But Monte Carlo doesn't include it is public. Whereas random walk does the opposite. So random walk starts from a certain point and kind of takes steps around that area. And so in theory, random walk is very good at if you start from a good spot, it'll do a good job of finding things around it at a spot. And so the idea is to kind of combine the two. So and so to do objective function, you would first run Monte Carlo for I wouldn't you usually don't want to overkill it. And so I think for part A, I have you run it for a maximum of like 100,000 or a million times.
Yeah.
And so you wouldn't want to do that. So maybe you want to do maybe like 1,000. So you take 1,000 random samples, you find the best one. You find the best out of that 1,000. Then you use that as a starting point for random.
Okay, so for instance, also what like another like topic is how would you be related to this topic?
Oh, like yeah, that would be really good. And usually I like to put the code in a separate window, so usually I kind of click and drag it down. Yeah, just so I can kind of view it side by side.
And even like
yeah, I guess I've never seen this actually. Maybe what is new? You try maximizing the whole video. Yeah, that is really my particular. Yeah, we define yeah. You click and drag. You can click and drag the workspace. Without here. You can have it in a separate window. I think there's a way to kind of like snap it to, because I think if you snap it to this area right here, it's gonna do a weird kind of coming in and out. But if you snap it to like this bar right here, it at least always stays present. Because usually what I like to do is I like to have the workspace open for these types, for these problems. Just because the workspace is gonna tell you, you know, the value for the.
Yeah.
And I have that open and I have the code open on the other screen.
Yeah, and that's what, like, it's like I said, I don't really like to use like, why.
No, yeah, no, it matters because you're going back and forth between the workspace and the code so often, so.
I guess I can probably. Yeah, okay, so. So. We run this, at the end of this run, after 1,000 runs, we're gonna get a X1 back. Yes. So after all this, we can say like our X1 and Y1 best, those are our optimal values, and then from the random.
So what we had was just.
That was random. Okay.
Yeah, same idea, yeah, so then you would run Monte Carlo, so this runs for a fixed amount of times, whatever it finds to be the best, like that'll be saved in X1 best and Y1 best. And so below this, you can copy and paste the code for random walks, so go after random walk. Okay, so if you kind of, well, let's look at the whole thing first. And so, you know, one thing for random block, actually the most important part is this ancient one right here, 5, 6, and 7, because this defines where you want to start with random block. And so when you're copying and pasting, so this is the main part of random block. So this is the main part of the house. You're gonna have to set some other parameters too, like the and stat length and stuff like that. But instead of initializing to this part, you're gonna initialize it from whatever you found was best from Monte Carlo.
Okay, so like, okay. So the way like I'm thinking about it is like so basically just reforming that. But then we also have like a from best in here, so I can do like from best prime.
No, actually you can just reuse the same thing. In fact, you can just even delete the full line like this and delete these lines right here too. Because with X1, Y1, D1 best, you've already found that out from Monte Carlo here. So that variable is already set. You don't need to set it again. Okay. And so basically from here, you have to define some parameters. So you have to redefine n, you have to redefine the step and the minimum step. That's it. And then from there you can just launch straight into the random walk here. Okay. Because X1, well in this case it's 4. X1, 2, 3, 4 best. It's already set to be whatever was best from Monte Carlo. Yeah. And then from there you just start. So this part here is the main part of random walk. You said, all right, so now that we've already done the Monte Carlo jumping, let's start walking from here and see what's going to be about. Okay. Yeah. Okay.
So this is out. So if we have our objective function, well, I guess we don't need the objective, right? Because it's going to be the same.
Exactly.
Yeah. So we need step length, minimum step. We don't need that.
No,
we have that.
Exactly. Yeah, that is already set.
And then, so okay, so this is kind of like what separates. This is like all of like our algorithm.
Exactly. Yeah.
Gotcha. Okay. That doesn't seem to do that. Okay. And I was just. Oh. I have enough to go on.
Okay. Yeah, give that one a try. That one's interesting. I picked that one, just because I think it'll help with the project too. But that's actually a really good approach to the project. Monte Carlo, it's great for that. So hop around, find a good spot, and then start something else. Random walk actually isn't really that reliable because it's so random. Monte Carlo works well because it at least stays in balance. Yeah, random walk doesn't say that. It just goes all over.
Oh, I remember you said with it random walk that like you could kind of get stuck in the valley.
All of them can kind of get stuck in the valley. The only one that doesn't get stuck, ironically, is Monte Carlo, because it jumps. But all of them are possible to get stuck in the valley. Random walk is just not very good because it's random. And so you could just kind of take steps kind of back and forth, which ends up kind of getting stuck. And so you can actually like Yeah, there's a lot of really interesting combinations at that.
Okay.
But doing a Monte Carlo and then doing either like a random walk or coordinate search or pattern search after that is usually a really good approach.
Okay.
And that's
Oh,
so
so
like an own solution for the final project. That exactly.
like combinable with that. Yeah, I know you said we're not allowed to use Monte Carlo or but a combination of like we can.
A combination.
Okay.
There's not pure Monte Carlo. So there should be some walk and some searching. You know? So a little bit Monte Carlo at first, just to get close, and then like maybe a pattern search or something to find the outcome. That's really good.
Cool. Okay, thank you so much.
Yeah. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there. One more week until Thanksgiving. Although it's going to be the week from hell for some of you because of all midterms exams, I imagine.
I don't like how you stack the two on top of each other.
Oh well, you know, because that's because I want to have work over Thanksgiving. That's why.
You split it up between the 2 days.
Well, I wasn't sure where we're going to be with the content, so I kind of pushed it. But yeah, I know next week's gonna be really busy. I know you guys are going to study a lot. But you know, after that's Thanksgiving, so that's good. You guys will be off, but I'll be grading Thanksgiving. Okay. And so with that said, today, the plan is to finish up our discussion of Nelder-Mead optimization. And so this is the last method that we're going over in our unconstrained section. Okay. And so the next thing after this is to go over constrained nonlinear programming. Okay. And so if you're following along with the lecture notes, I am skipping one. And so I am skipping lecture notes. I think it's like 7 or 8 or something like that. I think it's lecture note 7 on descent methods. So the reason I'm skipping descent methods is because descent methods they're not applicable to your final project. And so I want to make sure I get all as much content out to you guys that can help you with your final project. Because I know that once we're done with Thanksgiving, I think that's kind of going to be everyone's focus. Okay. And so with that said, the current homework assignment that is going to be the last one. So homework 5 is the last one that I have planned. I'm going to have an optional homework assignment after the Thanksgiving break, just to give you some practice and some additional examples with constrained optimization. But I'm not going to collect it. And so you can do kind of as much of it as you need to kind of help you out with the final project. Okay. So homework 6 is going to be after Thanksgiving, but it's going to be optional because after Thanksgiving, you know, we won't have any more exams or anything like that. I want you guys to just focus on the final project. Okay. Okay, and so today will be kind of a transition day. So I think we'll probably finish up Nelder-Mead maybe halfway through the class. And then after that, we're going to start talking about constrained methods. Okay. All right. Any questions that I can answer before we get started for today? Yeah.
So with the Nelder-Mead, you start with like the triangle and you're talking about reflecting it.
Yeah.
So is it basically, you know, to find the optimal solution, is it within that triangle? or
Exactly.
At one of the points?
Yeah, exactly. So we'll see today kind of how we reach convergence with Nelder-Mead. But basically the way it works is that, you know, once it kind of gets close to the optimum, the Nelder-Mead has a way to kind of shrink the triangle. And once the triangle kind of shrinks enough,
then it'll basically all the points will be on top of the optimal. Yeah, well, we're going to talk about that. Yeah. Mhm. All right. Any other questions before we get started for today? Remember, so the deadline for homework 5 is pushed back till Monday. Just because the last problem on the homework involved another meet, and I didn't think we could finish it until today. But after today, you should be able to do problem 4 on the homework. Okay. Nelder meet, I think, is the most complicated algorithm that we're covering out of everything that we've done so far. But I think problem 4 should be pretty quickly, guys. So because mainly what I'm having you do, because Nelder meet is complicated, but once you have a code written up, there's not much you have to modify within the code. You just have to swap out the objective function. So problem 4 shouldn't take you too long, but of course, if you have questions on it, just let me know. Okay, so let's go ahead and pick up where we left off on Tuesday. Okay. So actually, let me scroll up here a little bit. Okay. And so on Tuesday, we were talking about the Nelder-Mead algorithm. Okay. And so, so far, let's kind of recap kind of all the algorithms we've learned in this section. So we started with Monte Carlo. Monte Carlo is great. In fact, probably after this homework, it might be your favorite method. We did random walk. Random walk's kind of okay. It has a lot of issues, and so you generally don't recommend it for a lot of problems, but it can work in some cases. Then we did 2 more methods that are kind of closely linked together. We did coordinate search and pattern search, right? And so both of those kind of have the same same ideas. And so those 4 methods that we've gone so far, I would consider those to be kind of like the basic nonlinear programming methods. So every optimization class will cover those methods to some degree. Okay, so you've kind of gotten the essential reading for those topics. Okay? Nelder-Mead, of course, is kind of a step up from this. It's a little bit more advanced, but the reason I want to bring it up is that Nelder-Mead is pretty much industry standard, and so a lot of optimization packages within MATLAB itself and in Python, they use the Nelder-Mead algorithm. Okay. And in fact, one thing we'll do after Thanksgiving is I'll show you how to use actually some of the pre-packaged optimization functions within MATLAB. And probably the one that's most commonly used is the Nelder-Mead algorithm. Okay, so it's good that we're kind of learning how it works, just so that you kind of understand how to use that function. Okay. Okay. And so the way Nelder-Mead works is that it's kind of like a geometric algorithm. So it has a lot of geometric kind of insights, a lot of geometric intuition for it. Okay. Because the basic idea is that you're basically going to be maintaining something called a simplex in your problem domain, right? And so simplex being an n by 1, or excuse me, an n plus 1 sided polygon in n dimensional space. Okay. And so in 2D, the one that we most often use our simplex is a triangle. And in 3 dimensions, it's a tetrahedron. In 4 dimensions, that's a little bit harder to visualize because we live in only a 3-dimensional world. But so only if you can play a 4D chess, I guess. Okay. But basically, the idea is to kind of maintain n plus 1 design points and then steadily kind of kick out the worst one and improve upon it as the algorithm goes on. Okay. And so the idea is like this. And so, let me go ahead and kind of illustrate what the algorithm looks like. Okay, so let me kind of draw kind of what it looks like in 2D, just so you can kind of see. Okay, and so in 2D, we're going to start with a triangle like this. Okay. And so in 2-dimensional space, our n is equal to 2, so n plus 1 is 3. Okay. And just like before, let's say that we're trying to move, we're trying to move the simplex to, where this optimal point is. Right? Right? That's the goal for every optimization algorithm is to basically find the optimum point and get there in kind of a time efficient and reliable way. Okay. Okay. And so the way Nelder-Mead does this is it kind of moves, you can kind of think of it as moving the entire simplex. You're kind of moving the entire shape over to that optimal point. Okay. And the way it does that is by kind of kicking out or eliminating the points that are furthest away from the optimum, or the points that have the worst value, okay? And so the simplex is going to move by kicking out, by removing okay. And so by kicking out the points that are worst and replacing it with one that hopefully is better, right? And we kind of continuously do this, we're eventually going to get closer to the optimum point. Okay. All right. So let's kind of illustrate a couple steps of this just so you can kind of see what that is, right? So let me go ahead and label the points here. Okay. And so for our current triangle, we have 3 points, 1, 2, and 3, right? And let's assume for a second that this is a pure kind of convex function. So there's this one optimum, and everything kind of eventually points to that optimum. So we're not going to worry about any local minimum. Okay. Okay. And so out of our 3 points here, 1, 2, and 3, we can see that the one that's furthest away from the optimum point is point number 3, right? And so we're going to remove this one from the simplex. Okay. Let me go ahead and erase these lines here. And we're going to replace it with one that's going to be closer to the optimum point, okay? And so this is the operation that we talked about on Tuesday. So this is a reflection, right? And so in a reflection operation, we take the point that we kicked out and we reflect it across the centroid of the other points, right? And so between points 1 and 2 are going to stay exactly the same, okay? I have my eraser on for some reason, okay? And so that X right there is kind of the midpoint between points 1 and 2, the ones we're going to be maintaining, okay? And so if we reflect across this point right here, okay? Okay. So we basically find a point that's equidistant from the midpoint on the other side of the simplex, right? And so if we draw another point right here, okay? We'll call this point 4, right? Let's go ahead and redraw the simplex to have these 3 new points, okay? And so by doing that, we've basically redrawn our simplex, and our new simplex here is closer overall to the optimum point, okay? Okay. Let me go ahead and erase some of these other ones, but I'll keep all the points on the figure just so you can kind of see, you know, where we started and kind of how we got. Okay. Okay. So now we have this new simplex, and so our new simplex is 1, 2, 4. Okay. And so out of these points, you know, we have to kind of decide kind of what's going to be the best one to remove. So this one's a little bit unclear. And so it's going to be kind of based on your preference here, but it looks, at least visually to me, it looks like point number 1 is further away from the optimum. Okay, so let's go ahead and remove that one. And so we're going to remove point 1. Okay. Once again, we're going to find the midpoint of the points that are remaining. So that's going to be the midpoint between 2 and 4. Okay. And we're going to reflect point 1 across that midpoint. Okay. We'll call this point 5. We redraw our simplex, okay? And now our simplex is even closer than what it was before. Okay. All right, so let's go ahead and repeat this one more time, or we'll do it a couple more times so you can kind of see it, right? So now out of this simplex, and so now our simplex is comprised of points 2, 4, and 5. Okay. Now it's pretty obvious that point 2 is the one that's furthest away. Okay. So let's go ahead and eliminate point number 2. Okay. Just like before, we're going to reflect it across the line here. Okay. So this is going to give us 0.6. And so once again, we redraw our simplex, and now our simplex is even closer than it was before. Okay. All right, let's do one more just to just for fun. Okay. And so now out of these points, 4, 5, and 6, it looks like point number 4 is the furthest away from the optimum point. Okay. And so let's go ahead and eliminate that one. Okay. We're going to reflect. Of course, when you actually perform this reflection in the code, it's going to be a lot more precise, right? And so I'm just kind of just guesstimating kind of where the reflection would be. I think I generally did a good job, but you know, the lines may not be equally spaced, or you know, it may not be perfectly perpendicular, but you know, the idea is there. Okay. All right, and so if you compare where we are now, right? So this is our simplex currently. If you compare that to our original simplex, 1, 2, 3. Right, so this is our original simplex. Okay. We're a lot closer than what we were before. Right? And if we kept this up, and so if we kind of continued more and more, eventually, you know, this algorithm would converge on that optimum point. Okay. So, you know, so this is kind of a visual representation of how Nelder-Mead works, right? So you kind of maintain this, you kind of maintain the shape. You know, it's kind of easiest to visualize in 2D and 3D, but the same geometric concept applies in 4D, 5D, 10D as well. Okay, and eventually you're going to converge on that optimum point. Okay, and so by maintaining the shape here, and so we kind of solve a few issues that we kind of had with our previous algorithms. Okay. Okay. On the one hand, you know, because we're kind of constantly maintaining not just one design point, but multiple design points, right? Just naturally, we have a good sense of we have kind of multiple samples of the objective function in a relative vicinity. Okay. Because if you look at all the other algorithms that we had, we're only kind of saving or maintaining one point at a time, right? Monte Carlo, random walk, coordinate search, pattern search, right? We only had one, you know, one point, right? But by sampling kind of multiple points in the same area, you know, that kind of gives us a better picture in terms of kind of where exactly we are in the design space. Okay. Okay. And having those multiple samples is really helpful because then we kind of automatically get a sense of what direction that we should travel in. And so that direction was kind of a big, kind of important point for all the other, you know, all the other algorithms, right? And to think about coordinate search, pattern search, right? Finding that right direction was complicated, and a lot of times, you know, we're kind of just guessing to a certain degree, right? But with Nelder-Mead, that direction is kind of automatically specified just based on the geometry of the simplex, right? And so it's something that's kind of happens very naturally, and it's not something that we have to kind of forcibly impose. And so that direction is kind of a much more natural consequence of that. Okay. And by that same token, the other quantity that we kind of had a lot of trouble with specifying before was the step length, right? And so because of the geometry of the simplex, we have kind of a very standard way of telling us kind of how far we should step or how far we should move our simplex. Okay. Okay. Right. And so a lot of the parameters that kind of gave us headaches in previous algorithms are kind of just come out very naturally from the Nelder-Mead. And in fact, it kind of updates it in real time as well. Okay. So this is kind of what I was talking about earlier, that once you have a Nelder-Mead method implemented, it kind of just is one of those things that kind of just works for a lot of problems. You just have to kind of throw it at different problems. And just the way that its logic is designed is that it kind of handles a lot of that stuff for you. Okay. That's not to say, there are still some parameters and there's still some things you can modify, but even with the default parameters, it ends up working very, very well. Okay. All right. Any questions on this so far? Okay. All right. So let's talk about a couple other operations that Nelder-Mead can do, right? Because so far, what I've shown you here is just purely reflection. But Nelder-Mead has a few other operations built into it to handle different situations. Okay. All right, because in theory, the reflection is kind of the main part of Nelder-Mead, and so reflection should be kind of in theory the only thing that you really need. But for certain other situations that can either improve the convergence of Nelder-Mead, or maybe help it get out of a rut or get unstuck. That's what these steps are for. Okay. So let's talk about expansion first. Okay. And so expansion, like the name implies, it aims to make the simplex bigger, okay, geometrically. Because with the reflection operations, based on how it's designed, the simplex stays roughly the same size. After a reflection operation, the idea is that your simplex stays the same size. It's just kind of moved over to a different location. Okay. But there are situations where you actually want to expand your simplex and actually make it bigger. Okay. And so the way it does this, the way this is accomplished is that this basically takes the vertices of your current simplex and pushes it more outwards. Okay. And so the situations where we want to do this in is when a reflection operation goes really, really well, right? And so let's say that we've just performed a reflection, right? And so we reflected a point and we evaluate the objective function at that new point, and it ends up being really good, right? And so it ends up being way better than all of the other points in the current simplex, right? And so what that tells us is that, because that reflection ended up so well, we should try to search in that direction even further, okay? So an expansion is never done on its own. An expansion is always done after reflection operation. Okay. Okay. So after reflection, if the reflected point produces a new point that is the best in the simplex, best being defined by its objective function value, right? And so if it has an objective value that's the lowest out of all of them, okay, then what we want to do is we want to perform an expansion to kind of keep searching in that direction. Okay? And so the formula for the expansion looks like the following. So XE, okay, this right here is the expansion point. Okay? This is equal to gamma multiplied by XR, okay? Where this XR was the previous reflected point. Okay? And so that emphasizes the fact that we can only do an expansion after a reflection, okay? Plus 1 minus gamma times XO. Whereas XO has the same definition that we saw previously in the reflection, reflection formula. This is the centroid. The centroid of all the other simplex points, okay? besides the reflected one. All right, and so gamma here has a little bit less importance, but this gamma here is called the expansion coefficient. So that's a user set parameter. So you can set the expansion coefficient as long as it's greater than 1. Then this formula will work. Okay? So I think the default value that I put in the code is either 1.5 or 2. I'll have to kind of see. Okay, so both somewhere in that range is usually good. You don't want to set this to be too high. If you set it to be too high, then the algorithm kind of gets too aggressive and it kind of expands. Okay. Okay, so let me draw this visually to kind of show you kind of what that means. Okay. So let's say that we have our 2D simplex like this. Okay. 1, 2, 3. Okay. And let's say that on this simplex, point number 3 is the current or worst value, right? And so we're going to reflect this point. Okay. So we're going to cross that out. Reflect it over here. Okay. So this is our new point 4, right? And so after performing this reflection and we evaluate the objective function at point 4, and we find out like, oh, that's pretty good. That was a pretty good reflection there. And so let's keep going, right? And so if we expanded this, right? And so we reject this point 4, and we just kind of keep going in this direction. Okay. Now our simplex has been expanded, right? And so now our simplex is comprised of like that. Okay. So we expanded. On point 4. And so we performed this expansion because once we found 0.4, we found that it had a better objective value than both 1 and 2, okay? And so 0.4 was the best, right? And so since 0.4 was just found from a reflection, then we expanded it to try to improve the simplex even further, okay? Okay. Of course, you know, an expansion is not always going to lead to an improvement, right? Sometimes you find a really good point and you try to expand, but the expansion point may be not better than the previous, right? And so you have to make sure to check. And so if the expansion point and so after doing expansion, we're not forced to keep the expansion point. If it actually is not an improvement, then we just go back to the reflected point. Okay. And so you want to make sure you check that because not every time an expansion is going to lead to an improvement. And in fact, you know that if you just kept the expansion point blindly, that kind of what contributes to your simplex getting stuck. Okay. And so you want to make sure to check that, right? Most of the times an expansion is going to work, and you're going to just have a bigger simplex, but you have to kind of check to make sure that it actually needs to improve. Okay. Okay. And so you'll see that we'll have code for that in the example as well. Okay. Any questions on this? Okay. So that's expansion. And so we also have the opposite of expansion, which is contraction. Okay. So this is the third Nelder-Mead operation that we can do, right? So we've done reflection, we've done expansion, contraction is number 3. Okay. And of course, just by the name, this is when we do contraction, the simplex is made to be smaller. Okay. And you know, in kind of true form, so this we perform a contraction when the reflection that we did ends up not working out so well. And so this generally happens. And so when I say it doesn't lead to improvement, it means that even after reflection, the new reflected point is worse than all the other points in the simplex. Okay. All right, so the formula for the contraction point actually looks very similar to the expansion point, except the parameter, instead of being greater than 1, is going to be less than 1. Okay. Okay. And so XC, this is our contraction point or contracted point. Okay. This is equal to beta times XH. Okay. For XH here, this is the current worst point in a simplex. Plus 1 minus beta times XO. Okay. Or XO is still the same definition. So XO here is the centroid of all other points in the simplex. Okay. Okay. And of course, we have this beta parameter. Okay. So this beta parameter is something that's user specified. So that's something that you have control over. Okay. And so this beta here is the contraction coefficient. Okay. And it has to be less than 1 for this to work. Okay. So I think typical values, I think what you'll see in the example is that I use beta, about, I think 0.5. Okay, so that's pretty steep. Beta still has to be greater than 0, and so it can't be a negative number. So it has to be between 0 and 1. Maybe I should say that. 0 less than beta less than 1. Okay. And so hopefully the idea is that, by contraction, we're going to improve the objective function, because our simplex may have just been too big, right? And actually the optimum point is somewhere in the middle of the simplex. Okay. And so that's what this hopes to achieve, is that this hopes to achieve, maybe we should look kind of inside the simplex, and that's where our optimum is right now. Okay. All right. But we have the same conditions here as expansion, right? And so there's no guarantee that a contraction operation is going to lead to an improvement. And so we need to check if that's the case. Okay. Although contractions usually are a lot more successful. And so generally speaking, you don't see contractions failing nearly as much as expansion. Just with contraction, you're kind of more looking in. And so you're reducing kind of the area in which you're searching. Okay. So most of the time contractions are going to be successful, but you still should check if it's not. All right, any questions on contraction? Okay. All right, so that's we've done reflection, we've done expansion and contraction. There's one more operation, although this one is kind of a last resort. This is kind of this one doesn't happen that often in Nelder-Mead, but the last operation is called a shift. Okay, so a shift operation is kind of a last ditch resort to improve the objective function. And in fact, this is the way that Nelder-Mead actually helps it get unstuck. Okay, and so a shift takes your simplex and actually shifts the majority of the points. Okay. And where we shift them towards is that we shift it towards the current best point in the simplex. This is the only operation that moves multiple points at the same time, right? So all the other operations, the reflection, the expansion, and the contraction, those only move one point at a time, right? Shift is actually going to shift multiple points. Right? So that's kind of what helps it kind of get unstuck. Okay. And so when do we perform a shift? A shift is only executed when a contraction operation fails to lead to an improvement of the objective function. Okay. All right, and so the formula for the shift is actually quite simple. And so we're basically just going to take for every point in the simplex, except for the best point, we're going to just take the average, okay, plus x plus xb. Okay. So xb here is the best point in the simplex. Okay. And these xi here are all the other points. Okay. So you're going to execute this for every point in the simplex except for the best. I guess technically you can do it for the best point too, but it's just not going to move because it's it's just staying where it is. So in other words, we basically just have the distance. So we have the distance between where that other point is, and we just bring it closer to the best point. Okay. And so in some ways, you can consider this to be a contraction operation because we're bringing all the other points closer to the best point. It naturally is going to shrink the entire simplex. Okay. But it's more of a dramatic contraction than kind of the other contractions. Okay. 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 So those are 4 operations. Yes, question. Yeah, you can definitely do that too. And so for kind of standard nailed meat, if your reflection doesn't lead to an improvement, you can try reflecting the second worst point instead. And sometimes that can help kind of break you. But usually that happens when you're kind of stuck in a valley. And so if you reflect the second worst point, then it kind of gets you out of that valley, and then you can kind of continue from there.
I have a follow-up question. How can we tell when to do that?
Yeah, no, it's and that's some freedom in terms of how you can implement the Nelder-Mead. So for a lot of Nelder-Mead algorithms, they'll try the second reflection. They'll kind of always try the second reflection. So they'll try reflecting the worst point. If that doesn't improve, they'll reflect the second worst point. If that doesn't work, then they'll try the contraction. If that doesn't work, then they'll try the shift. So that's kind of usually the chain of actions. Some Nelder-Meads will only do the second reflection if certain other conditions are met. Maybe if the only when the simplex is a certain size. That has some considerations as well, because sometimes if your simplex is too small, if you reflect, then you're not really going anywhere. And so then you're probably close to convergence as well. And so there's a lot of flexibility, a lot of freedom in how you can implement this. Mm-hmm. Okay. All right. Any other questions on this? Yeah.
It's very similar. So we have 4 different types of operations.
Mm-hmm.
I assume in the code, is that like written in an if statement, like before?
Yes.
Okay.
Yeah. Well, we're always going to do a reflection. And so we're always going to try a reflection first. And so that's what you're going to see in the code, that there's going to be a loop. And then at the beginning of the loop, we're going to have the code for reflection. And so we're going to try that first. And then if that works really well, then we're going to do an expansion. And then if we did an expansion, then we just go to the next reflection. But if it didn't lead to improvement, then we have the contraction. And if that doesn't work, we go do the shift. And so, yeah, there's a lot of if statements in that code. Yeah. But every time we try to do a reflection, that's kind of the standards. Any other questions on this? Actually, I think that's a good idea. Let me write that down. So the general. Actually, I think I started writing this last time, but maybe I guess I just got sidetracked. General steps. Okay. And so this kind of already assumes that you have a simplex, right? And so the starting point for an Nelder-Mead operation is to start with a simplex, okay? And so from your simplex, the first thing you're going to try is to try to do a reflection of the current worst point okay? Okay. And you can have a step 1B, I guess. So I don't think I have this in the example code. But I think in the example code I don't reflect the second worst point. But you can try it here as well. Okay. Okay. For higher dimensional problems, I've seen them even try, reflecting the third worst point, fourth worst point. But at that point, it's kind of, if it didn't work the first 3 times, then it's, you kind of get into insanity, right? Trying the same thing and expecting a different result. So, okay. And so based on the outcome of the reflection operation, you then move on to the next steps, okay? So if reflection, I should say, led to dramatic improvement, and so if it leads to a point that's better than the rest of the points, okay? And so if we get a point that's better than the rest, then that's when we do an expansion, okay? And so we want to keep searching in that direction, basically, okay? On the other hand, if the reflection did not lead to an improvement, then we're going to perform a contraction. Okay. Right. And then if the contraction fails, then that's when we perform a shift. So that's kind of the logic of Nelson. Okay. And so when you break it down like this, it's not too complicated because I think when people look at Nelson-Mead, you kind of get bogged down with a lot of the geometry that's involved, a lot of the equations that are involved. But this is kind of the logic of Nelson-Mead, and then you kind of fill in the details of the equations from there. Okay? And so when we break down the code, I want you guys to be looking out for these steps. Okay. There is a fifth step. It's not an operation, so don't worry. So we're done with all the operations. And so the fifth step is to check for convergence. Because at some point we have to exit the algorithm. We can't just keep moving our simplex at infinity, right? And so we have to have a criteria for kind of stopping the algorithm and saying that we found an optimum. Okay. Okay. And the way that we do that is the following, right? And so the Nelder-Mead operation is said to converge when the standard deviation of all the simplex points falls below a certain threshold. All right, and so one last formula. Okay. And so I'm explicitly writing out the formula for standard deviation. But of course, if you're using a code like MATLAB, using a code like Python, you know, MATLAB has its own functions for computing standard deviation. So I think that's what I do in code. Okay. Okay. And so the formula for standard deviation looks like the following. So I have 1 over n plus 1. Okay. Summation from I is equal to 1 to n plus 1. Okay, because that's the number of points we have in our simplex. We have f of xi minus f of x naught. Okay. Squared. Okay. And so we sum up these squared quantities, and then this whole thing we take the square root. Okay. So that formula that I have in the middle there with summation, that's the formula for the variance of the data set. Okay. And so if you take the square root of the variance, then you get the standard deviation. Okay. So don't worry about this formula too much. This is not something you're going to directly input in the code, because in the code, you know, you're just going to say compute the standard deviation of this. And so once the standard deviation falls below a certain threshold, okay, so this right here, this epsilon is our convergence threshold. Okay. Once that happens, then we'll have conversion. So our algorithm is done. Okay. So that's the last thing we're going to check at the end of every iteration. Okay. Because we don't want to keep iterating if we're already done, essentially. Okay. All right. Any questions on this? Okay. All right. So that's the whole algorithm. And so let me give you an example problem. So actually, let me write out what the objective function is here before we jump into the code. Okay. So let's minimize the following. Okay. And we're going to use Nelder-Mead. Okay. And so our objective function here, f of x1 and x2. So you have just a 2D problem here. Okay. You have x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. All right, and so to start our Nelder-Mead operation, we need to have initial simplex. And so here, I'm just going to give it to you. Okay. And so since this is a 2D problem, we need 3 points in our simplex. Right? So we have x1. So x1 here is going to be 4.0, 4.0. Okay. x2, that's going to be 5.0, 4.0. Okay. x3 is 4.0, 5.0. Okay. So those are the 3 initial points in our simplex. So we're going to form basically a triangle between these 3 points. Okay. Okay, and so the other parameter values that we have is alpha. So remember, alpha is the reflection parameter, and so we're going to set that to be 1.0, pretty standard. Beta is our contraction parameter, and so beta we're going to set to 0.5. Okay, again, very standard. Gamma was our expansion coefficient. Okay. And so gamma we're going to set to 2.0, again, very standard. Okay. And then the last parameter that we need to specify here is our convergence threshold, epsilon. Okay. And so for this problem, let's use epsilon equal to 0.1. Okay. Okay. And so now we're going to go over the implementation in the code. Okay. So the example code I've posted on Canvas, and so you can kind of view that as well. Okay. So what I've done is I've just downloaded it, and we're just going to view it here in the lecture. Okay. Any questions on this example before we jump into that? Okay, all right, so let's take a look at that, let's take a look at that example. Okay. So this is the example that we have here, okay? And so this code here is called, what is it called? It's called UNLP example 5 nailed or meet, right? And so it's the fifth example because it's the fifth algorithm that we've done over. Okay, and so let's go ahead and set our parameters here. So first, let's set capital N. So capital N is going to define the maximum number of iterations, okay? And so this is another nice thing about nailed or meet is that you can set an overall cap on it. And so you can tell it to stop after a certain amount of time. Okay. Ideally, the algorithm is going to stop once it's converged on a solution, but you can also just force it to stop after it's done enough. Okay. We have little n, and so little n is going to define the dimensionality of the problem. And so since we only have two design variables, we have n is equal to 2. Okay. Okay, and so you can see here that I've defined two vectors here. So I have xi and fi. Okay. And so these vectors are going to be important because these are going to be what's going to store our current simplex values, okay? And then fi is going to define the objective function values at those simplex points, okay? And so we need to keep track of both. And so this is, remember, this is different than all our other algorithms because in our other algorithms, we're only tracking just one point at a time. In this algorithm, we're tracking, n plus 1 points, right? And so since our n is 2 here, we're tracking 3 points at any given time, okay? And we're saving it in a vector here just to be, just to make things convenient for us. Okay, and then here we're going to define all of our other parameters. And so we have alpha, beta, and gamma, okay? And so I guess I was a little bit aggressive here. And so, let's go ahead and change this back to 0.1, like we said in the class just now. But you can play with that convergence threshold and see how the solution changes from there. Okay. And so this next part of the code right here, we're going to be defining our starting simplex, right? And so these are going to be the 3 points that we just kind of wrote down in the class. And so we have 4, 4, 5, 4, and 4, 5. Okay. And so for each of them, we're going to define their point. We're going to evaluate the objective function at that point, and we're going to save the point and the objective value in our simplex. Okay. So actually, let me leave a comment here. And this saves the objective value at this point in the simplex. Okay. And so we need to do this for every point in our initial simplex, right? And so, for n is equal to 3, or n is equal to 2, then we have 3 points that we're evaluating here. Okay. Okay. All right, and so because we have a lot of if statements here, I'm creating what I'm calling flags. Okay. And so these flags are going to determine whether we're going to perform expansion, contraction, or a shift, okay? And so I'm initializing all of these to false, right? And so these values will be updated throughout the algorithm, but we need to keep track of these in case we need to perform an expansion, a contraction, or a shift, okay? You'll see how these are used in a second. Okay, so now we start the nailed or meet operation, okay? And so you can see the first thing that I'm starting here is I'm starting with just I'm checking convergence. Okay, so I guess this is a little bit opposite from what I did before, or what I just showed you in the class, right? And so instead of performing a reflection, I'm just checking for convergence first, right? And so by convergence, what we're doing is we're checking the standard deviation of our objective values, and so that's what this formula does here. Okay. And so instead of implementing that kind of large stuffy formula for the standard deviation, we're just using the MATLAB STD function. Okay, probably the most unfortunately named function in MATLAB, but that's what standard deviation is. Okay, and so if we're not converged, then we can go on and proceed with the rest of the algorithm. Okay. Okay, and so the first thing we need to do is we need to find the current worst point in the simplex, right? And so the way the reflection operation works is that we're reflecting the current worst point, okay? And so the worst point here is defined by whatever the maximum objective value is, right? And so remember, for these problems, we're always doing a minimization. And so actually a larger value of the objective function is actually worse, okay? Okay, and so you can see from the tooltip here, we're using the MATLAB function called max, okay? And so what max does, and if you feed it a vector, it's going to tell you two things. So it's going to tell you both the value of what the entry was, as well as the index, okay? And so this index is probably the most important thing, because the index is going to tell us which simplex point, is the worst one. Okay. Okay. And so that's what the max function does. And so now with that knowledge, we can go ahead and proceed with the reflection. Okay. Okay. And so before we do the reflection, we need to compute the centroid, okay, of all the other points. And so this is x naught, right? And so what we're going to do is we're going to save this vector here, right? And so we're going to loop through all of our simplex points, and we're going to save each point here. The only exception is that if we're going to skip over the worst point, okay? Because remember, the centroid that we compute is everything except for the worst point. Okay? And so when we're performing this for loop here, if our loop index k, if that is equal to the same thing as the worst index, then we just skip it, and so we just continue. Okay. If not, then we keep adding to the centroid here. And at the end, we divide by the total dimensionality, and so x naught is going to be the centroid of all those points. Okay. Okay. All right. And so now that we have the centroid, and now that we know that we need to perform a reflection, let's go ahead and perform that reflection here. Okay. And so you can see here that I'm defining a new variable xr, right? And so that xr is going to be our reflected point. And so you can see that this is the formula for the reflected point that we defined previously, okay, in the lecture. And you can see that this part right here is important, because this is going to give us the current worst point. Okay, so that's the point that we're eliminating. Okay. And so not only are we computing the coordinates for that reflected point, we're also computing the objective value at that point as well. Okay, so that's what this line of code does right here. Okay. Okay. And so now that we have performed our reflection, now we need to kind of assess. Okay. So now you can see here we have three if statements. Okay. Okay. And so the first thing we're going to check is we're going to check and make sure that our new reflected point, FR, actually led to an improvement of the objective function. Okay. So this checks. Previous worst point. Okay. All right, and so we save the objective value at the previous worst point. Remember, we saved that in the variable called worst value. Okay. And so if FR is less than worst value, then we just simply accept that point, right? And so we add it to the simplex. Okay. And then we also save its objective value. So these two lines of code right here basically replaces the old worst point with the new reflected point. Okay. All right. And so in most cases, this is hopefully going to be true. So this is going to be our reflected point right there. Okay. Okay. Now we need to check and see if we need to perform an expansion or a contraction. Okay. And so remember the conditions for the expansion. So we perform an expansion if our reflected point is better than all other points in the simplex, right? And so if FR is less than the minimum of FI, right? Where FI is the collection of all of the all the other points in the simplex. Okay. If that's true, then we're going to perform an expansion. Okay. But if FR is greater than or equal to the worst value, or if FR is less than the worst value but less than the other, or greater than the other ones, right? And so in other words, what this if statement checks here is that if the reflection did not lead to an improvement, okay, and so it's either the reflected point is the worst one, or it's, only slightly better than before, okay, then we're going to perform a contraction, okay? As you can see here, the way that I'm kind of signaling this is I'm changing these Boolean values from false to true, okay? And so before these were false, and so now they're true. We need to perform an expansion or a contraction. Okay, so that's probably the most complicated part of the code, right? And so the most complicated part is actually the reflection and kind of deciding what you want to do after the reflection. Okay. Any questions on this? Yeah, it's a lot of stuff, and so this is probably the most intense coding that we've seen, by far, actually. Okay. Okay. But from here, it's pretty straightforward, and so here we just kind of have more straightforward code, for the expansion. Okay. And so if the improvement was great, then we're going to perform an expansion. Okay. And so you can see here that this is the formula for the expanded point. Okay. And then we're also evaluating the objective function at our expanded point, okay? And if this led to an improvement, and so if the expanded objective function is less than the reflected point, then we save it, okay? And then from there, we reset the flag to false. So this is important. This is important so that on the next iteration, we don't kind of perform an expansion. All right. So that's the expansion. Here's the contraction, okay? And so for the contraction, we're going to define our contracted point based on this formula here. Okay, so this formula is in the notes, and then this FC here is that's going to be the objective value at the contracted point. Okay. And so just like before, we're going to check to see if this is an improvement. And so if it led to an improvement, then we can save its point. If not, if the contraction didn't lead to improvement, then we're going to perform a shift. Okay. And then just like before, we're going to reset this flag to false. Okay. And then finally, the last thing we have here is the code for the shift. Okay. And so this is kind of perform the shift. And so remember, for the shift, we need to find the current best value. Okay. And then we're going to move everything closer to that best. This moves. Okay. All right. All right, and so that's the 4 operations for the Nelder mean. Okay. So it's a lot of code. So by far, I think this is the longest code that we've looked at. So this is 131 lines of code. Okay. But a lot of it is a lot of the logic and a lot of the complexity comes with the reflection. Okay. And so if you can kind of get the reflection down, if you kind of understand that part, then the rest of it kind of falls in line. All right. Any questions on the code before we try running it? Okay. All right. So let's go ahead and run the code. And so you can see here that the optimization converged in 19 iterations. And so it took 19 loops of the for loop in order to converge. Okay. And then where is our X best here? So our X best, where do we save it? We saved it in a variable called X opt. Okay, so let's look for X opt. Okay. Okay. And so you can see that the best values for these parameters is X1 is equal to -1. And X2 is equal to 52. Okay. All right. All right. So it's 5:08, and so I definitely don't want to start something new in the last 5 minutes of class. So I'll stick around a little bit, just so I know some of you guys are still working on homework 5. And so if you have questions on homework 5, I'll stick around for the next 5 minutes and answer that. If not, then you guys are free to go for today. Okay. And so this is the cutoff for the midterm. So we're going to start covering new stuff on Tuesday, but the stuff we cover on Tuesday will not be on the midterm. Okay. So the last thing you're responsible for knowing for the midterm is Nelder mean. Okay. And with that said, you know, for those of you who kind of stuck around to the end today, I'll give you another nugget of information. Because the Nelder-Mead code is so long, you know, I know I talked about on Tuesday that, you know, there's going to be some pseudo coding questions on the midterm where I give you kind of some code segments that you have to tell me kind of, you know, fill in the blank and tell me what's the logic behind it. I'm not going to put Nelder-Mead on the exam for the coding question because, you know, it's a little bit too long. So, you know, we'd be killing a little bit too many trees if we try to put this on the exam. So, I'll give you guys that as kind of a nice piece of information sticking around to the end. Okay. But you should still understand Nelder-Mead at least from a conceptual point of view. And so you know, I will likely ask you a conceptual question, just a short answer to a 2 or 3 sentence question on Nelder-Mead on the exam. But in terms of the pseudocode, in terms of filling in the blanks and understanding this code, I'm not going to put that on the exam. There's a question in the back. Yes, next Thursday, so a week from today. Yeah. All right, so thank you guys for coming today. Hope you guys enjoy your weekend, although I know you guys are probably studying really hard this weekend. So good luck with your studying. If you have any questions about anything, just send me an email. And all of my office hours next week are available for you to come and ask questions as well. Okay. All right, so thank you guys for coming. I hope you guys have a good weekend, and I will see you guys next week.
Just want to, just 3D.
Yeah.
The angle for the 315, yes, it's fine.
Yeah.
Okay, that's fine.
B or C?
I'm sorry.
Should be C.
Yeah, it is C.
Yeah, C
nice.
is B.
Because B is gonna be, yeah. Thank you. Yep.
Wait, what is that? Oh, the hanger. Dang. It's hard to tell like how big it is from the picture.
Yeah, no, it's huge.
Wow.
Is that code right now?
Yeah.
I worked down the street, you know. Yeah. Do you know where it was? They haven't released the report yet. Thank you for.
Oh, of course. Yeah. You too.
Yeah, there was a nice glow when I drove by on Tuesday morning.
Oh, you're saying that's the one that burned down? Yeah. Oh
I
my
worked down
god.
the street.
Oh my gosh. Dang. Was there a lot of smoke from it?
It wasn't blowing towards us.
Okay.
Yeah, no, we're right.
Oh my gosh, that's crazy.
That's the north one. We got the south hangar just up the street from us. It's we're on Cardinal,
Yeah.
which hangs into Tuscan Ranch Road, and it's right there across from
Oh,
Legacy.
wow. Dang.
It could be the homeless. They're trying to keep warm.
Very warm, I guess.
And they got away from them.
Could it really start that big of a fire though? It had to be something internal, right?
Well, because they camped out inside.
They're actually inside the hangar. Oh, okay.
They've caught them in there before.
Oh,
So
I see.
not hard to jump the fence.
Yeah, that's true.
Because I took that from Armstrong.
Oh.
And I was like, you should have been there. Wow, right. All the asbestos and whatnot.
That sounds like I shouldn't be there.
Well, because they were built in the early 40s, so they didn't have all the.
Right, yeah. And burning asbestos, I don't want to be there. All right, Zong, any final questions before I wrap it up? Okay, all right, see you next week.